The topic of this presentation is time domain VSWR and chamber debugging. Quick introduction. The time domain VSWR is a method that's described by C63.25.1. And this method basically talks about the time domain site VSWR site qualifications for chambers or alternative test sites above 1 gigahertz. And this is presented as an alternative method to the CISPR 16 site VSWR method. The first question I want to address is why there's another VSWR method, because site VSWR method described by CISPR is already an established method. What's the reason to introduce another method? It turns out the time domain VSWR method has several advantages over the traditional CISPR site VSWR method. First of all, it's a much less time consuming compared to the CISPR method. And also, that's not the main reason. The main advantage is really about the test repeatability and lower measurement uncertainty. So this method would give you much more repeatable measurements and also reproducible measurements. And the other additional benefit is that using time domain VSWR to measure chamber performance, it gives the indication where the site may be deficient and thus allowing the debugging and using corrective measures to bring the site into compliance. So this is the main thrust of this demonstration, is that we want to give a demonstration of how one might use this method to debug a failing chamber. Site VSWR is required to qualify an anechoic chamber for above 1 gigahertz measurements. And as I mentioned earlier, this is part of the CISPR 16-1-4 standard. The concept of the site VSWR method described by CISPR is based on using a probe antenna, which is omnidirectional. In this case, actually a transmit antenna in CISPR measurement. Because of reciprocity, it really doesn't matter. But in this case, that antenna is an omnidirectional antenna. You can move along a linear line to sample the standing wave in the chamber. So this is very similar to how we traditionally do VSWR measurement in a slotted line. One of the requirements is that the antenna omnidirectional is because we want to illuminate the chamber walls as much as we can. So this is, like I said, similar to a transmission line measurement, and except in this case, in the reflections is not as simple as just a one-dimensional reflection. And there are actually reflections coming from many different surfaces. So as a result, your standing wave is a lot more complicated than a simple wave pattern like you would see in a traditional transmission line. This is a CISPR site VSWR test setup illustration. So people who are familiar with this test can probably recognize this chart. You've seen this in many different occasions. You can see the receive antenna illustrated here as a double ridge waveguide antenna. But that antenna can be any antenna that you typically use for doing emissions measurement. And on the other side, the other antenna is required to be omnidirectional antenna. In this case, is illustrated as a mini biconical antenna, which is most of the antennas for these type of tests utilize this kind of antenna. This is an illustration that's obtained by simulation, is the standing wave along a transmission line at 2 frequencies. When I move that transmit antenna along the length, so the standards require you to move along a 40 centimeter distance. So that's why you see there are 6 dots. Those 6 dots represent the 6 positions that you would measure the site VSWR. And those are the 6 red circles you see. For a chamber situation, the standing wave is really complicated. Even for 1.5 gigahertz, you don't really have a nice and up and down standing wave pattern. And as you go higher and higher frequency, even at 6 gigahertz, you can see how complicated that standing wave becomes along a linear line. And the problem with the traditional site VSWR method is that you're using those 6 points and you're trying to capture the true maximum and true minimum of that standing wave. It's a really difficult situation to be in, and most of the time you don't truly get that peak maxima and peak minima. So as a result, you don't really truly capture the maximum standing wave. So that's why one of the biggest issue with the traditional method is that your site VSWR is undersampled and the value is overly optimistic. So that's a compromise in the CISPR site VSWR method. And this is not, the standard committee doesn't really know that using these few points along a short distance is undersampling. This is really a compromise to save test time and complexity, because if you are familiar with this test itself, if you follow through the whole process, because the number of points, number of positions, and number of heights and polarizations involved, this test is a long, tedious test already. To be able to sample this without undersampling, that is just impractical. And that's why also those 6 points are those 6 irregular positions. And the other compromise that the standard made is that the minimum frequency step is 50 megahertz. And I will show later in a chart that the 50 megahertz is another problem in that it's also undersampling along the frequency domain. So these compromises made SVSWR less accurate and less repeatable. And this is really a major concern for this type of test. So this is the example to show that frequency undersampling. So this is actually true VSWR measured in a chamber based on CISPR 16-1-4. And you see 2 lines on the chart. The only difference between those two is one is the frequency step is 49.5 megahertz, and the other one, the frequency step is 50 megahertz. And you can see the difference between these two is one is a passing test, and they're exactly the same chamber and same exact test setup. Based on C63.25.1 time domain VSWR, so I just give a quick introduction of what this method is about and how you would obtain this. And most importantly, I want to show there is really a correlation between these two methods. So using the time domain method, instead of moving the receiving antenna to plot the standing wave, what we do is we actually take a vector response measurement in the frequency domain. So the one thing I want to stress is this measurement is still in the frequency domain. So when you measure the S21 as a function of frequency, if you have the vector response, that response can be transformed into time domain via Fourier transform. So this is where the time domain comes in. The data acquisition is still in frequency domain sweep. To be able to do the Fourier transform, unlike the traditional site VSWR method, we have to obtain the vector response. We have to have both magnitude and phase. And then once you get the information in time domain, so what you get is an impulse response between two antennas as a function of time. Then you can apply time gating to measure the VSWR of the chamber. The whole process measurement method as far as test setup goes, except not moving the antenna, we don't need to move to the 6 spots. Everything else stay the same. The type of antenna, the polarization, heights, and this is by design because we want to establish a correlation between the two methods. And so the time domain VSWR method is developed so that it can be closely correlated to the CISPR site VSWR results. And the additional benefit is really about time saving and more accurate and more repeatable. And then later on, we'll show that method. We can also debug a failing chamber or find out what's wrong with a failing chamber. So this is an illustration of the method. On the left side, there's a picture in the chamber with a site VSWR setup. This is a horizontal polarization. And what you're measuring, shown on the right, is the S21 measurement. Of course, this one is only show the magnitude, but we also obtain phase information when we use a vector equipment, vector network analyzer, for example. And so once you grab this data, for that position is really about post-processing at this point. So then we take that information, we do a Fourier transform of that S21, and on the left side, you can see the blue line represents the time domain transformation of that S21. So now the response is actually an antenna response as a function of time. You can think of this as you're sending an impulse from one antenna, and what would be the received signal be from the other antenna? Because any reflections happening is going to happen after the main antenna response, because the main antenna to antenna response is the first thing, has the closest distance. All the reflections would have to come from a farther distance because it needs to bounce off something and come back to the antenna. And so the first impulse you can see on that graph is really the main antenna-to-antenna response. So what we're interested in for the time domain method is that what would be the response as if all the reflections don't exist. Mathematically, we could easily do that applying a time domain gate. And the green line here represents the time-gated signal. So mathematically, I can remove these reflections. So if we only take that information, we can have the response as if the antennas are in free space without these reflections. Conversely, I can delete this main response and then only look at the reflections. So in this case, I apply a filter that's a band stop filter. And so what I call here a gate out. So in this case, it's gate in this case, it's gate out. So this is, of course, still in time domain, and I can easily transform this signal from time domain back to frequency domain. That's what the next slide shows, is that if I do a gate in operation, so this is red line is the original signal. If I apply this gate in, only look at the antenna to antenna response without the reflections, the smoother blue curve, which is the gate in information. And on the right hand side, this is the when I notch out antenna to antenna response and only look at the reflections. So this curve here represents all the contributions from the reflections in the room. So now I have the reflections and I have the antenna to antenna direct responses. So the next step, we take a ratio of the two in terms of linear units. In dB, it would be a subtraction. So if we take the gated out signal over the gated in signal, and that would give us the reflection coefficients. So this is really the definition of a reflection coefficient, right? The reflection level versus the main signal level. And so this is reflection coefficient. Of course, in the VSWR method, all the standards and the metric is in VSWR. So this is a pretty easy conversion. We all know from our textbook from VSWR and to reflection coefficient. This is the equation to convert the reflection coefficients back to VSWR. So over here, you can see this is basically the blue line would represent SVSWR calculated by this equation. So in here, I also drew a line that's a running average with a sliding frequency window. And if I take all these rapid changes, this shows the overall trend. Because the site VSWR based on the CISPR method has this undersampling issue, and it's really difficult to compare one-to-one to look at the VSWR from these two methods, using the time domain versus using the traditional moving the antenna method. So because the CISPR method is really a undersampled set of data versus the TD method is not undersampled, as you can imagine, the TD data most likely is going to show a much worse chamber result. But if we do a moving average of the two to look at the trend, so this is actually obtained in a real chamber measured by both the time domain method and the CISPR method. And if we do this moving average to look at the underlying trend, and these two methods is really correlating to each other. So we know deep down that we're really measuring the same physical quantity using either the time domain method or the CISPR method. As we talked about earlier, time domain data looks a lot more erratic, and you can see the data is also probably worse in terms of chamber performance. The reason is really two reasons we mentioned earlier. We want to be able to correlate the severity of the current standards to the time domain method. In the end, the CISPR method is a well-established method and is well accepted. If a current chamber today passes the requirement, when you use a new method, you really want to make sure that we're gauging the same chamber with the same kind of severity. So this next few slides will explain how we achieve that. So the time domain, as you saw, what I call is more erratic. And if you take that data, subtract the TD VSWR from the moving average, of course, now the data is going to be centered around zero because we subtract the underlying trend. This is what you see on the left side. you can see this data almost look like a Gaussian noise. You can see the signal goes up and down, looks sort of like a noise. But this is not noise. The data is highly repeatable. If you don't move the antenna, you don't move the test setup, you run it again, you would get this chart exactly back. It's very repeatable. It's basically determined by the reflections in the room. If I plot this data and do a histogram of this moving TD VSWR subtracted by the moving average, and you can see this data actually looks like a Gaussian distribution. So this gives us a hint of, okay, if the data is really Gaussian noise-like with a normal distribution, maybe we can use statistical metrics to describe a site VSWR, and then we can, say if we want to change the severity of the requirement, I can basically use a different coverage. For example, I can cover, people doing uncertainties are familiar with this concept of 2 sigma covers 95%, and 1 sigma covers 67, 66%. So this is the same thing. If we can adjust the severity coverage, we can match the severity to the current standard. So this is a blow-up picture. So I zoomed into a specific frequency range. What you see is the SVSWR on the vertical axis, and the x-axis is the frequency in hertz. For example, over here, I'm looking at between 1.1 to 1.25 gigahertz range, and I say this is my sliding window. The standard requires you to look at a sliding window of 120 megahertz. And you can see all these data, this is the real data before you do any processing. And I have a moving average of this area. And also within this moving window, I can calculate what the standard deviation would be between the TD VSWR subtracted by the moving average. So I have a standard deviation and also I have an average. And now I can say, okay, if I'm interested, instead of 100% or 99% coverage, which you would probably do, is you have the moving average at, say, 3 sigma. This is probably going to cover all the peak in this area. But if I don't want to cover 100% of the data, I can have a smaller sigma standard deviation, and then I would be able to adjust the severity. For example, if I just don't add any standard deviation on top of this moving average, we know from statistics 50% of the data is going to be below that and 50% of the data is going to be above that. If we add some sort of a standard deviation, then of course we can adjust this line up and down. And there we can establish a time domain VSWR with a severity that's not 100%. And there we can maybe match up with the current severity. The final time domain VSWR is determined by this equation, is the moving average plus 0.676 sigma. So this 0.676 is the knob I was talking about earlier to adjust the severity, and this actually corresponds to a 75% of coverage. So another way to look at the time domain VSWR with this equation is we're saying that 75% of the points you measured is going to be under the reported value. So this final TD VSWR is what we're saying is there will be 25% of data that will exceed that. From a statistical point of view, it's also interesting to look at the current CISPR method. Is if the two is shown to be equivalent, what you're saying is we're covering 75% of the test points. That's under the limit of 6 dB. If a chamber is right at 6 dB, and that would mean 25% of the data probably are exceeding that 6 dB requirement. So this is a conceptual change for a lot of people because people thought their chamber measured below 6 dB, all the data points are below 6 dB, and that's not true. This is just an example showing a measurement in the chamber. Later on, when my colleague Anoop running the test, he will show you an actual measurement in the chamber obtained by the time domain VSWR method. And this chart is interesting to show because we can see the time domain method. If you look at the overall trend and level based on this green line, 75%, 6.76 sigma, is very similar in severity compared to the traditional CISPR method. This process we talked about looks kind of daunting because you have to take a Fourier transform, and then you have to do these equations, you have to apply this moving average, and then you have to do this statistical analysis. The good news is that all that can be automated. This is a one-button operation, if you will. If you're interested, you can download the scripts from the standards website. Most of the popular analyzers, you can really just download a script and run it on a script. The whole process I described is done in the background because the time domain transformation and the statistical analysis, time domain is a function that in a lot of network analyzers. So the script would take advantage of the analyzer's capability to do that transform, and all the post-processing of the analysis of the data is done by the script. So you will see this process when my colleague running the test, we're not doing these kind of calculations by hand. Back to the main theme, we want to show you how one would be able to use the whole measurement process to debug a chamber, a failing chamber in this case. So what you see on the screen is a VSWR of a chamber. Look at the red line. So the red line is the time domain VSWR you would obtain using the described method. Obviously at 2 gigahertz, this chamber is above the 6 dB limit. So this is a failing chamber. Now, normally, if you use a traditional VSWR method, you wouldn't have any clue of why this chamber would be failing. So this is a head-scratching moment now that you don't know what to do. How do we know what's wrong with this chamber? Time domain can help you with finding out what the problem might be. And we obtain S21 between two antennas. So in this case, when I go back to this chart, this is a, I'm not sure what position. For example, this is at the top of the quiet zone, front position. And you take this S21 measurement. You can take that S21 measurement and then transform it into time domain. So this chart here is a time domain view. It's not labeled here on the x-axis. The label should be time in seconds. 10 to the minus 9, so that's in 10 nanosecond step. So you can see around, say, 1 point, actually in this case is 15.8 nanoseconds. At that step, there is the main antenna to antenna response. So we all know wave travels at the speed of light in free space environment in air. So then, the speed of the wave is 3 times 10 to the power of 8 meters per second. And that turns out to be roughly 1 nanosecond per foot. That's pretty convenient. If you think of this as 15.8 nanoseconds, so this is roughly 15 or 16 feet away between the two antennas. So obviously this is not the front position. It's probably on the side because the front position is close to 3 meters. So you can see this is about 4 or 5 meters, probably one of the sides. And so you can see this is main response between the two antennas. And then we can see there in this chamber, we definitely have quite a few reflection points in the chamber. We don't really know which one is going to make this chamber fail. So of course, in the post-processing, this is fairly easy to do. We can say, let's try one at a time. We can go look at this one is a reflection. We can manually delete this reflection mathematically, right? At this point, it's all post-processing. We don't even need to go back in the chamber anymore to do this. We can say, okay, let's delete this reflection mathematically, and then we can transfer back and to see what the VSWR would look like. And you go through the same process and get the VSWR. If this is the one that would be dominating, or this one would change the chamber, make it compliant, obviously this is the one we need to deal with. So at the same token, you might not find that immediately. You can try several other places. In this case, most likely you're going to try the second one because it looks pretty big, this reflection. We look at delete that, it really didn't make the chamber pass. It's actually this one. The reason that these levels are not exactly corresponding to large reflections may not necessarily correspond to the large contribution for that frequency is that in time domain, the signal is actually a convoluted signal with all the frequency information in it. So we don't really know that large reflection might be occurring for different frequencies. So that's why we have to kind of trial and error to find out what frequency that one is dominating that reflection at that frequency. So in this case, you can see, okay, that actually the reflection that would make the chamber fail or pass is actually this reflection at 24.5 nanoseconds away. The difference between the main antenna-to-antenna response versus the one that's a reflection that we need to take care of is actually about 6.7 nanoseconds. And so that is roughly about 8.7 foot. What we're saying is the reflection compared to the direct antenna-to-antenna response is 2.6 meter longer. And so we know the antenna-to-antenna direct response is 4.1, so that corresponds to the 4.1 meter in this case actually corresponds to this 15.9 nanoseconds. That's the distance between the two antennas. And so we know from that antenna added to that path, the total path length. So we know the path length compared to the direct path is 2.6 meter longer. So the total path for that reflection is 6.7 meter. In other words, if I send this pulse from the transmit antenna, it hits some wall and bounces off that wall, goes back to the other antenna, that whole path is about 6.7 meter. What do we do with that information? So if we go back and look at this chamber, in this case, we use a ray tracing tool, shows the possible rays between the transmit antenna and to that position. And then we can see there are a lot of rays in this chamber that can bounce. If you think of you're shooting a pool and shooting a ray bounce off of some wall, there are lots of bounces. But in this specific setup, there are only two possible rays that can have roughly this type of distance, roughly around 6.7 meter long. Those two passes, and one is this one here. So this is actually bouncing off a back wall and then this side wall. No, I'm not exactly sure. This is bouncing off the ground and the side wall into the other side. If you can rotate it, when my colleague is doing the presentation, he'll rotate around and let you see it. This is a little difficult to see because you kind of lose the 3D sense of it. And the other one is this possible bounce. It bounces off the ground and side wall and then into the quiet zone. It's pretty much narrowed down to these two possibilities, and we go back in the chamber, then we figure out, okay, this is actually the one that's causing. We knew it ahead of time because we actually intentionally took out an absorber over here to make this chamber fail. And then, of course, when you fix that problem and remove that reflection point, and then we rerun the test, this chamber now is in compliance. Instead of scratching your head, you can really analyze the time domain information and use that information to help you debug a failing chamber. The couple of observations is TD and CISPR VSWR methods, they show close correlations. And the CISPR method underreports the data because of these two undersampling issues in the spatial domain. And again, it also undersamples in the frequency domain. So either of these issues are not problems with the time domain method. And so the CISPR method, you're really undersampling. It's like finding a needle in a haystack. You're always going to undersample somewhat. And that's why the traditional SVSWR is also very sensitive to small changes because you're so undersampled. When people move the absorber slightly or when they take the measurements, the antenna is slightly tilted or the cable is slightly oriented differently, it can really mean a pass or fail. And versus the time domain method, because it's done in a statistical sense, you can't really change the underlying moving average and the standard deviation very easily by making small changes because these are statistical properties. And the time domain method, most importantly, not only it's faster, quite a bit faster, as you will see from the demo. Literally, you set the two antennas down, you push a button, wait for a second or two, a couple of seconds, boom, you got the site VSWR of that spot. And most importantly, it's repeatable and also gives us this ability to debug a chamber. I don't need to belabor these points. And less uncertainty, faster test time, and also debugging And these are the reasons that really highlights the benefit of using a time domain method to do a site VSWR measurement. In fact, we do a lot of site VSWR measurements at ETS-Lindgren. Most of the time when we go into a chamber, first thing we do before we run the traditional VSWR, if that's required by a customer, we always run the time domain first to just get an idea of could there be potential problems. Because when we launch into the CISPR method, that's a long, tedious process. In the end, we can only know the results after this long data collection process and find out if there is a pass or fail. Versus in the time domain, we can quickly go in there and see if there is any issues. And then if everything looks good, if it's required that we need to run the traditional CISPR VSWR, and then we go into running that test after we're sure the chamber is probably going to be a passing chamber with the time domain information.
Hello everyone, my name is Anoop Adhyapak. I'm a senior RF engineer at ETS-Lindgren, and right now we'll switch to the demonstration section of the time domain site VSWR chamber debugging program. So here we have our FACT3 chamber. It's a 3-meter chamber, and we already have set up the test setup. So we have the EHP12 absorbers on the floor, on the ground plane, and then we have our 3183B, which is a mini bicon broadband antenna from 1 to 18 gigahertz, and then we have a 3117 over there as a receive antenna, which is also again from 1 to 18 gigahertz. Both are set at 1 meter's height. So usually in a site VSWR test, inside an EMC chamber, we would generally test at multiple locations, right? So we would test it at center location, front, left, and right. Right now we will be conducting the test only at the front position, so that it's easier and fast. With regards to the test setup, we've already hooked up the cables to the network analyzer. We've set the network analyzer frequency settings from 500 megahertz to 20 gigahertz. Even though our test is limited from 1 to 18 gigahertz, we would actually increase the frequency span just to take care of the gate edge effects. So that's why we'll be sweeping it from 500 megahertz to 20 gigahertz. Because we are using a Keysight PNA analyzer, we have the liberty of choosing 16,001 points. So we're going to choose the max as 16,001 points. The IF bandwidth is already set at 1 kilohertz. Our output power is set to 0 dBm, and then we already conducted the response through cable calibration just to mitigate any losses or reflections due to the cables. So now we will step out of the room, do the frequency sweep, and do the time domain site VSWR for the front position at this 1 meter height for vertical polarization. As you can see from the screen on the figure, that the red line is our passing line, which is supposed to be the 6 dB criteria as per ANSI C63.25 and CISPR 16-1-4 standards. So for the front position at 1 meter height and vertical polarization, we achieved a time domain site VSWR result of no worse than 5 dB. So as you can see from the screen, that it basically took only 10 seconds to conduct this test for one position. If we compare this technique to our conventional CISPR 16-1-4 method, we had to do 6 locations at every position, and each location would be about the same amount of 10 seconds of sweep time. So we basically reduced our test time from 6 positions to only 1 position using this method. So since our goal of this demonstration is to show how to debug a failing chamber, so I guess now the next step would be for us to get inside the chamber and try to fail the chamber. What we'll do is actually we'll take a metal plate and we'll probably try to put it at some specular reflection points on left wall or right wall or even on the back wall, and we'll try to see exactly how this metal plate putting at these specific location can actually hurt the chamber performance. Once we do that, then we'll repeat the test again, and we'll see exactly what kind of result we get, and then we'll go from there. So we already installed the metal plate on the back wall of the chamber, and now we'll run the test again. So that's it. Okay, we got the test result. This definitely looks extremely odd and extremely bad in terms of the chamber failure compared to our baseline measurement, right? So if we post-process this data as well, we can again have a look at our time domain view of the data. This is also our gate in data of the chamber, and this is our gate out data of the chamber, and this is the corresponding time domain site VSWR result. So here, I guess now the next thing which we have to look for or decipher is which reflection is actually failing this chamber. Obviously, we already know that we have installed a metal plate, and that's why we have such a bad chamber performance. But then in a real world scenario where, as Zhong showed in the presentation, where we actually took out an absorber where it represented a bad absorber on the wall or a deteriorated absorber performance at some location, one way to look for or try to find that would be actually go back to this time domain view, and then if I expand this, and then we have to probably apply another notch filter at these individual reflection spikes, right? So we already have applied a notch filter to the direct antenna to antenna response. So maybe we need to add another notch filter to these different reflection peaks to see exactly which one affects the chamber performance. So to find exactly where my chamber is failing, I need to gate out individual reflection spikes, and then see exactly which reflection fails my chamber or improves the chamber performance, right? So then with regards to that, I'm gonna try this peak first here, where I'm gonna say, okay, for example, the time corresponding to this reflection spike is 14.25 nanoseconds. I'm gonna go in my code, in the post-processing code, I'm already set it. I'm going to run this test and see what I get. Okay, so this still fails. This chamber still fails. Now, if I look at this gate out data, I can see that obviously I've already applied a notch filter to my direct antenna to antenna response, as well as the notch filter to this reflection spike. But then obviously applying the notch filter here did not help. So maybe we can try a different reflection spike. Let us look at this. So this corresponds to 28.86 nanoseconds. So I'm going to feed that in the code, and I'm going to run this again. Well, this still fails, right? So this still fails even with this. So definitely it's not this reflection either. So okay, let's look at this guy only. So this is at 25.97 nanoseconds. Okay, so this literally passed the chamber. So definitely we've found our culprit, wherein once we notched this reflection spike, it actually made our chamber like it was before. So if I compare this result with our original baseline measurement, result what we had. So that's the comparison, right? So this the middle figure is the time domain site VSWR result without any metal plate inside the chamber. That was our baseline reference. And then this one is with the baseline, is with the metal plate on the back wall, but then we've already applied a notch filter mathematically, and then we found, and then we calculated the time domain result. So as you can see, they both of them match very well, pretty much almost the same. There are some discrepancies which could be again due to the time gate settings of the notch filter. So okay, so finally we found exactly which reflection spike is actually hurting our chamber. So now what we can do is we can go back at our time domain view, right? And now let us calculate exactly where would be this reflection point in the chamber. So this is, as we know, this is our direct antenna to antenna response, right? And then if I create a new data tip to find this the time for this reflection spike. So now I know that the difference between the two I need that to calculate the total path length of the reflection spike. So this is 25.98 minus 11.35, which comes to 14.63 nanoseconds. So if I feed that in a simple Google result to calculate from light nanosecond directly to meter, or you can also do this, convert the 14.63 nanoseconds, which will correspond to almost 14.63 feet, and then calculate that in meters, which will approximately come to the same number. So I know that this extra additional length is 4.38 meters with respect to the direct antenna to antenna response. So my total path length of this reflection would be 4.38 plus 3 meters, which will be about 7.4 meters.
So now that we have found the exact distance or the exact path length, now we'll go back inside the chamber to actually find out that particular reflection point inside the chamber using a string, basically. So here we have a string which has the length of the total path length, right? And then we're going to attach one end of the string to the transmit antenna, another end of the string to the receive antenna, and then we're going to move this string so that it will basically touch either of the walls. If we go to the left wall, you can see that the string is not straight. It's probably still it's hanging, so that means it kind of tells us that this path length is too long for a reflection from the left wall.
Now if Martha moves to the right wall, you can see that the string is extremely long to have a reflection on the right wall. You can see that Martha is moving the string, the extra length of the string, and then definitely that tells that the reflection is not occurring at the right wall.
So if we go to the back wall, you can see that the back wall, it touches it perfectly at this particular spot, which tells us that the reflection has to be at this spot, and this is exactly where we kept our metal plate. We pinpointed the reflection point using the string method, right? Another approach to find the reflection points is a little more technical.
So what we'll do next is we'll actually we will come back and try to feed in model the chamber in our chamber simulation tool. So here is our proprietary tool developed by ETS-Lindgren for the chamber simulations, and then we've already fed the chamber dimensions and the antenna locations respectively inside the chamber. So here you can see that definitely here is the transmit antenna 3183B placed on the edge of the turntable at the front position, and then the pink dot represents the 3117, which is the receive antenna. So we simulate this antenna, this chamber, to actually do the ray path tracing, and then we have a tool here to actually get the ray path files, and we can look at that. So if I load my ray path files, so this is the ray path file for my low position, for the front position. So here in this you can see that definitely these are the different bounce numbers. So when it says bounce 0, it corresponds to the direct antenna to antenna signal, right? This is the ray path for the direct antenna to antenna response. Similarly, these are the different bounce number ones, which corresponds to the first order specular reflection inside the chamber from all the individual walls. So here you can see that this is from the side wall, and then this is from the ceiling, another side wall. So based on our calculation, the total path length of the reflection was 7.38 meters, which corresponds to this reflection on the back wall. So yeah, this is knowingly we know that definitely we have placed the metal wall on the back wall, metal plate on the back wall, and we can actually find the exact spot of that reflection also. So definitely using this tool we can find out exactly where could be the reflection spots inside the chamber. So for example, in another instance, say for example the reflection spike which you calculated from your time domain, it would have come out to around 8.5 meters. Well, in that case you would have had multiple candidates with respect to this ray tracing over here. As you can see
that you have 8.5 meters distance over here for this reflection path length. You have another reflection here which has a path length of 8.37 meters, and there's another one over here which is about 8.58 meters. This is also another candidate for 8 meters distance. So here you can definitely see that if your reflection occurred at around 8.5 or between 8 to 8.5 meters, these would have been your several candidates. Now, obviously, we would have to analyze one by one on exactly how and which reflection would actually make an impact. If we start looking at all of this one by one, this corresponds to the front wall reflection, wherein it's saying that this reflection is received by the receive antenna from the back lobe of the receive antenna. So this is probably a highly unlikely reflection which is going to impact our chamber performance. Similarly, if you go ahead, so this definitely could be a candidate because you have a reflection on the side wall onto your back wall, and then from the back wall onto your side wall and then to your receive antenna. Similarly, on this one, this is also a second order bounce from your back wall to side wall to your receive antenna. So and this reflection would be from your side to side wall. So these three definitely could be the candidates to look for or to work on if your reflection spike path length came out about between 8 to 8.5 meters. But as in our example, we already calculated that the path length was 7.38 meters. We definitely know that it was this. We can definitely narrow it down to this particular reflection spike, and then say like, okay, this is the spot where the exact reflection is occurring, and then we can get inside the chamber and try to put some absorber around, on that spot and around it to see if that makes a difference in the chamber performance. So definitely the advantage of this tool is that we don't have to do the troubleshooting process inside the chamber, wherein we can actually sit at our desk and do the post-processing and then figure out exactly which are the culprits with respect to the reflection spikes, and then go inside the chamber to improve the performance. So I hope everyone enjoyed the presentation and this demonstration. I hope that from Zhong's presentation, everyone understood the basic understanding of the theory, and then from the demonstration, you also got to know the intuitive approach of the application and its benefits with regards to the real world applications. So I would like to thank my colleague Zhong for his valuable inputs, and then I hope you all enjoyed this demonstration. Thank you.